Hey, welcome back to Calculus. We're going to keep working in section 2.3 here. In this video, I'm just going to try to rip out some examples of how you compute limits using the limit laws that we looked at in the previous video. All right, so let's just get going. Our first example here, you can take a look at it. I want to take the limit as x goes to 5 of that rational function, x squared minus 25 over x minus 5. This is a 0 over 0 limit. You can check, stop the video, both the numerator and denominator of that expression are 0 when you let x equal 5. So we got a factor. This is just like our previous lecture video, the final two examples. The denominator is already factored. It's just a linear polynomial. The numerator is a difference of squares. So it factors into x minus 5 times x plus 5. And if x is not equal to 5, then you can cancel that common factor. So when you do it, if x is not equal to 5, you're just left with x plus 5. And now you can evaluate that limit by just plugging in 5. So you get 5 plus 5, or 10. All right, I've got some graphs set up over here. We can take a look really quick just to kind of illustrate. So what did we just compute? We just computed that on the graph of this function, x squared minus 25 over x minus 5, when x is very near 5, 5 is not in the domain of this function. Yeah, you cannot plug 5 into that thing. You get 0 over 0. It's a meaningless expression. But if x is arbitrarily close to 5 on either side, then the y values on that graph should be close to 10. All right, so let's switch over real quick here. I hope this isn't too annoying to switch to my Desmos window. I think it can happen pretty quick. So I'm switching over, and now you're looking at my Desmos window, and you can see up here in the corner, I've got the formula, x squared minus 25 over x minus 5. Maybe you're surprised by this graph. The graph looks like a straight line. Why does it look like a straight line? Well, because in the computer software, it's just plotting points, and it didn't plot the point x equals 5. So it looks like 5 is in the domain. But if I were drawing this graph on a piece of paper, right here, when x is 5 on that graph, there should be a little hole in it there, because x squared minus 25 over x minus 5 does not have 5 in the domain. But if x isn't equal to 5, it agrees with the function x plus 5. So that's what we're looking at here. We're looking at the line y equals x plus 5 with a hole in it. And sure enough, this confirms that at x equals 5, very close to that input, the y coordinates are close to 10. So that's what we just computed on the whiteboard screen. Okay, let's switch back, compute another one. Coming back here, doesn't take too long. Let's do a second example. This is also a 0 over 0. They all the interesting ones are. If the denominator doesn't go to 0, you evaluate a limit by plugging in. So I'll take a sip of tea here and let you check that if you plug h equal to 0 into the numerator or denominator of that expression, you're going to get 0. So we have to cancel that common factor. This time the cancellation won't really come about immediately by factoring, but rather by squaring out that top. We need to multiply out that 2 plus h. Notice how I keep writing my limit symbol until I quote unquote take the limit, until I let h equal 0 in some expression, until I can use that direct substitution property. It's very important that I keep writing this out here, because when I'm saying two quantities are equal, they really need to be equal. Okay, so expanding out that 2 plus h squared, let's see if I can do it. It's 4 plus 4h plus h squared, and then we're of course subtracting 4 from that. And now in this numerator, I have a 4 and a minus 4, so they additively cancel each other. So if I sort of bring this down, again, I'm still writing the limit as h goes to 0, and the numerator 4h plus h squared, I'm actually going to factor out an h out of that. So you can pause and check my algebra, but if you distribute that h back through there, you'd get 4h plus h squared. And now we can see that factor that's making h equal to 0 cancels. This cancellation is valid as long as h is not 0. So if I rewrite this thing one more time, I haven't taken the limit yet, so I keep writing my limit symbol. But now I'm at a place where I can use the direct substitution principle. Yeah, I'm not going to divide by 0 if I let h equal 0. So this limit is 4 plus 0, or 4. all right? So if we looked back at a graph of this function, if I looked at a function 2 plus h quantity squared minus 4 over h, near h equals 0, I expect the output coordinates of that function to be equal to 4. And we can switch back to Desmos real quick and take a look at that. This might be the last switch we do. It takes a little time and makes the videos longer, but I think it's important to kind of reinforce this graphical stuff. So now you can see over here, I've got the function. Desmos wanted me to call the input variable x. So just read this x as an h. It's my 2 plus h quantity squared minus 4 over h. And you're again looking here near at 0. There's a hole in that graph at 0. X equals 0 is not in the domain of this function, but the output coordinate we can clearly see is equal to 4 when x is near 0. So that confirms the limit that we just took. Okay. I encourage you, while I'm switching back, let me say this out loud, when you're computing these limits, you're taking this course online, hopefully you've got a computer next to you, I want you to plot as many of these things on Desmos as you can and just graphically reinforce what this algebra is telling you. In fact, it's a good mathematical habit of mind when you're understanding something algebraically, have some way of thinking about it graphically. And when you're thinking about something graphically, have some way of understanding it algebraically. Use those two things against each other and it'll severely deepen your understanding. Okay, but here, I promised short focus videos. Let's just keep going. I've got another limit to compute here. I'm just illustrating some techniques. This is also 0 over 0. I'll let you check it. If you let t equal 0 in the numerator and denominator of that expression, in both cases, in the numerator, you're going to get 6 minus 6. In the denominator, you get 0. So how do we factor something like this? You can't expand a square root. So I'm going to just sort of show you an algebraic technique that you can use to eliminate this. We need to eliminate this t down here. It's the reason I can't just do this by the direct substitution principle. Okay, so I'm going to multiply this fraction by 1 in sort of a sneaky way. I'm going to take that expression in the numerator, square root of t plus 36, but I'm going to add 6 instead of subtract. Okay, so this expression that I'm multiplying by, maybe you remember it from a high school pre-algebra class or pre-calculus class or something like that. It's called the conjugate. I've multiplied by the conjugate, but I had to multiply by the conjugate in the numerator and the denominator because otherwise I'm changing the expression. Yeah, so when you multiply by a non-zero number over itself, that's just equal to 1. So you don't change the expression. So now let me show you with some algebraic manipulation why the conjugate is going to help us do this. If I multiply, say, in the numerators, are you guys focusing with me? I have to multiply these two quantities together using the binomial expansion, the FOIL algorithm. So the first thing I'm going to get is the square root of t plus 36 times itself. Well, the square root of t plus 36 times itself is just t plus 36. Okay, and then what am I going to get? I'm going to get negative 6 times that square root and a positive 6 times that square root. That's why the conjugate is kind of nice. I'm going to write it, but those cross terms will always cancel. That's what switching that sign does. So I'm going to get negative 6 times that square root. I'm going to get positive 6 times that square root. Finally, I have to multiply negative 6 by positive 6. That's going to give me minus 36. So there's our numerator before we simplify it. In the denominator, I'm not really going to try to simplify this thing at all. I'm just going to write t times the square root of t plus 36 plus 6. But again, why I multiplied by the conjugate is because in this numerator, these two terms cancel each other additively. They're the same with opposite signs, okay? There's more to do up there. There's a plus 36 and a minus 36. Those things cancel additively. So if we kind of stop and regroup, I think I have enough room to do it here. All right, that's the limit as t goes to 0. In the numerator now, all that survived was t. I've got a t plus 36, there's square root, plus 6. And now, multiplicatively, if t isn't 0, I can cancel those things. Yeah, so my final expression that I have after all of that cancellation happens, got 1 over the square root of t plus 36 plus 6. And now you can verify that the direct substitution principle will work. That denominator doesn't become 0. When you plug in t equals 0, it becomes 1 over the square root of 36 plus 6. That's 1/12. So I'll leave it to you to check out this function on Desmos on your own. But if you plotted the function t plus 36 under a square root minus 6 divided by t, when the input coordinate is close to 0, as t approaches 0, the y coordinates on that graph are going to be close to a 12th. Okay, so this conjugate trick, you can keep it in mind whenever you have an expression that has a difference or a sum involving a square root or even two square roots. You can change the sign. That's what makes it the conjugate. Multiply by top and bottom so that you don't change the expression, and see if this cancellation will work out for you. All right. There's one problem on your activity for this section that you're going to use the conjugate. Okay, let's keep going. Trying to get you into the habit of checking denominator then numerator. So here x is going to 5 in this rational function. 5 makes the denominator equal to 0. Okay, so then I check the top. 5 does not make the top 0. It makes it 12. So this is not a 0 over 0. So when this happens, when the denominator approaches 0 and the numerator doesn't, it's going to be an infinite limit. It's going to be an infinite limit because x plus 7 does not approach 0, but x minus 5 does approach 0. I'm just using some sort of shorthand over there as x approaches 5. Okay, whenever that happens, the limit's not going to exist in some sense. Because you're dividing a non-zero number by something approaching 0. So it's going to get infinitely big or infinitely big in the negative direction. You have to use the signs to see which one. So when you're doing this, you want to use one-sided limits. You want to use one-sided limits. We want to take a look. What happens as x, say, approaches 5 from the left? Well, again, the denominator is becoming 0, and the numerator isn't. So it's going to be plus or minus infinity. So we just have to think about what the signs will be. So if you're approaching 5 from the left, if I drew a little picture over here on the number line, approaching 5 from the left means I'm taking values that are less than 5. Well, then x minus 5 is going to be negative. X minus 5 is going to be negative. When you're a number near 5, x plus 7 is around 12. It's positive. So when x is very close to 5 but on the left, this ratio is the ratio of a positive number over a negative number. So that limit is going to be negative infinity. It's going to be negative infinity. How about the one on the right? The limit as x goes to 5 from the right. The numerator is still positive. It's still about 12. But when you're coming into 5 from the right, if you're picking values of 5 that are, values of x that are bigger than 5, not values of 5, x minus 5 is positive. Yeah, if x is bigger than 5, then x minus 5 is positive. So this is going to be a ratio of a positive number over a positive number. So it's going to be positive infinity. Okay? So when the numerator does not approach 0 and the denominator does, then you don't have a limit. So negative infinity and positive infinity, they're different signs. So up here, the best we can say is, well, this limit doesn't exist. The limit doesn't exist because the left and right hand limits are not equal. And in particular, they're not both positive infinity and they're not both negative infinity. All right, so the limit doesn't exist. Let's take a look at a picture. It's all ready to go for us. Doesn't take too long to get over there. Here I've got it graphed, x plus 7 over x minus 5. You can see it on the left-hand side of the screen. It's graphed in green. And sure enough, we can see that at x equals 5 itself, we have this vertical asymptote. I don't know if Desmos will let me just draw. Yeah, there you go. It drew it in blue. And we can see what we just computed algebraically. If we take x and let it approach 5 from the right, the y coordinates on this green graph are becoming more and more infinitely negative. Yeah, if x approaches 5 from the, sorry, I said the wrong word. X approaches 5 from the left, values that are less than it, then we're going to negative infinity. The y values on this green curve are negative and growing down without bound. Okay, if x approaches 5 from the right, the y coordinates on the green curve are all positive and they're growing up without bound. So that's what we were just algebraically calculating on the previous screen. Okay, all right, let's keep going here. I hope these examples are useful for you. I hope you're going to do all those problems in the activity and also in the textbook in this section, and check your answers on Slader or come to my office hours and talk to me about them, because this is really some business that you can get confident at, but you have to practice it. You have to practice. You have to do a couple of dozen of these things before you start getting the hang of these calculations down. Okay, so I've got a couple more here. Let's see if we can just do them. So we're taking, this time it's the limit as x approaches 2. So my habit is to check the denominator, and sure enough, the denominator goes to 0. So then I check the numerator. The numerator is going to go to 1/2 minus 1/2. That's also 0. So this is a 0 over 0 limit. So we need to do some canceling. And this time, basically, we just have to kind of get a common denominator and simplify this numerator. We've got a complex fraction here. So let's organize our work like this. I'm going to start by, instead of dividing by x minus 2, I prefer to think of division as multiplication by the reciprocal. So that dividing by x minus 2, I'm going to write it like multiply by 1 over x minus 2. All right, so I hope I have enough room here because I didn't really need to use all that space for that line, but that's just sort of a general tip I have for you, that instead of division, why not just multiply by the reciprocal? I mean, we're better at multiplying than we are dividing. Now, in these parentheses here, 1 over x minus 1 over 2, I'm going to get a common denominator, and the common denominator I'm going to get is just 2 times x. So I multiply the first fraction by 2 over 2, multiply the second fraction by x over x, and that would be my common denominator. Okay, so I get 2 minus x divided by 2x. And now, well, you can probably already see it, but I'm going to write it explicitly. This 1 over x minus 2. 2 minus x is just the negative of x minus 2. So now we can see finally that pesky factor that was causing everything to be 0 cancels. If x is not equal to 2, x minus 2 over itself is equal to 1. So after we make that cancellation, I'm still writing my limit. I haven't taken it yet, but what do I get? Negative 1 in the numerator, and there's a 2x in the denominator. And now by the direct substitution principle, we can just let x equal 2. 2 times 2 is 4. So that limit is minus 1/4. Okay? So sometimes the cancellation has to come about from getting some common denominator if there's fractions involved. All these examples I'm showing you where we have a 0 over 0 limit, in some sense, you have to do some algebra. Maybe it was common denominators, maybe it was using a conjugate, maybe it was factoring, maybe it was expanding, but you have to do some algebra until the reason the denominator is 0 cancels. Okay, that's basically the gist of all of these examples. Let's do one more. I think one more. Yep, this is it. Example 6 is the end. So what do we got here? 1 over x minus 1 over x squared plus x as x goes to 0. Both of those expressions are not defined when x is 0, so we can't use it in this form. So let's get a common denominator. Let's see what happens if we say try to take the difference of those two fractions. So the common denominator, again, I'm just going to use the product, x times the quantity x squared plus x. So multiplying the first fraction by x squared plus x, the second fraction by x over x, we would get something like this. Now in that numerator, I can see that x and minus x cancel additively. So I'm going to take advantage of that. Then what do we got? We've got, well, x squared in the numerator. Downstairs, we've got an x. And if I factor an x out of x squared plus x, okay, so then I can see that I've got an x squared downstairs and an x squared upstairs. And as long as x isn't 0, which it's not, because I'm taking a limit as x approaches 0, so I don't have to worry about that value. Those things cancel. So what do we get? We get the limit as x goes to 0 of 1 over x plus 1, and now that's ready for the direct substitution principle. That's going to be 1 over, well, if you want me to write the details, 0 plus 1, that's 1 over 1, that's 1. So if you took a look at the function 1 over x minus 1 over x squared plus x, it's not defined at 0. You can't plug 0 into that function. 0 is not in its domain. But if x is arbitrarily close to 0, the y-coordinates on that graph will be arbitrarily close to 1. All right, so there's 6 examples that I hope give you some ideas. You can watch this video as you're doing your homework in the section 2.3, and I hope it's helpful. Thanks for listening.